So next, we're going to hear from Dr. Will Fox, and he is going to be one of our user spotlight sessions. I've asked Will to come in somewhat with a quick turnaround of time, as we had a session we wanted to fill here with a particular kind of user research example. And Will's title to his presentation is Exploring Fundamental Physical Processes for Astrophysical and Space Plasmas at the National Ignition Facility. So let me give you just a brief background on Will. He's a staff research scientist at the Princeton Plasma Physics Laboratory. He's been there since 2013, and his research interests include plasma physics with applications to space and astrophysical plasmas, fusion energy, and high energy density plasmas. And primary among these are magnetic reconnection, a fundamental plasma process which allows the fast conversion of magnetic energy into plasma kinetic energy, including the acceleration of particles to very high energy. So as he's into his presentation, I know he'll be describing more of that particular focus, and I will not try to explain much more of plasma physics in advance of his presentation. Will, let me welcome you onto the screen.
Hi, thank you everyone very much. Thank you, Dan, for inviting me today. You guys can hear me okay?
Yes.
All right, great. I'm going to share my screen here. Can you all see my presentation?
Yes.
Great. Yeah, so today I'm going to talk about our work to do plasma astrophysics experiments in the laboratory using some of the laser facilities around the US. My team and I have had a set of campaigns at Omega and NIF over the last few years. And we're using these to generate plasmas and collide them and show how energy gets transformed from one state to the other in these plasmas. And the overall goal is to understand some of the most explosive phenomena that we see out in the universe, and understand it by understanding the fundamental processes behind it in the plasmas. So yeah, as Dan said, I'm a researcher at Princeton Plasma Physics Lab. I'm also a lecturer at Princeton University, and we've done this set of experiments at Omega at University of Rochester and at the National Ignition Facility at Livermore for the past few years. I'm going to try to keep it at a pretty high level, since I think this is a pretty broad audience. Feel free to ask any questions that you want about it as we go along. Okay, so these are very collaborative experiments. There's a huge number of people involved on the facility side, and also scientific collaborators involved in these experiments, and I'd just like to acknowledge them before we get too far into it. In particular, a few of my science colleagues, Derek Schaefer at Princeton, Mike Rosenberg at University of Rochester, were really instrumental in getting these experiments to run at the NIF. They had this role called the NIF SHOT RI, or responsible individual, which means that they were responsible for actually implementing it on the machine, all of the details of it, which was really an enormous job. Also, several graduate students from Princeton have been involved. A great project for a lot of them has been to, at that point in the project, was to do simulations to help design these experiments. And I've highlighted them as well. This work has also been supported on the funding side by Fusion Energy Sciences and a Department of Energy and NSA joint program that funds research in high energy density plasmas such as this. The experiment time is funded through facilities such as NIF Discovery Science and the NNSA National Laser User Facility Program. And we've had computation time available through DOE via the INSIGHT or ALCC programs. So overall, it's a large thank you to all of the other scientists who participated in this, and the facility staff and scientists, and this vision for collaborative science. So yeah, the overall goal is to do laboratory experiments to study fundamental dynamics in plasmas, to understand how plasma energy gets converted from one form to the other. There are several processes. Magnetic reconnection, which I'll talk about today, is a process that converts magnetic energy to particle energy by rapidly dissipating the magnetic energy. There's other processes that we're also studying over the past few years. One is collisionless shocks, which is a phenomenon also out in the cosmos where you rapidly convert plasma flow kinetic energy into particles and heat. There's also anisotropy instabilities that are related to if the plasma is highly out of thermal equilibrium, where it's hot along one dimension and cold along another. This can excite very violent instabilities in the plasma. There have been many other experiments as well on plasma turbulence and plasma dynamo, which are about how you convert plasma energy to create magnetic field. So there are all these processes that happen out in the universe that convert energy from one form to the other. And laser experiments at NIF and Omega provide some very unique capabilities towards studying these processes. A main thing is that we want to get plasma conditions that are sufficient to match some of the relevant dimensionless parameters we think from plasma theory are important for understanding these phenomena. Second, these experiments have very high quality and high resolution diagnostics that let us observe these phenomena both at global scales and then down at kinetic micro scales in the plasma. And I'll come back to a little bit more definition of what these mean as we go through. So our experiment campaign at NIF, which I'll talk mainly about today, is studying magnetic reconnection. And we've gotten into something that we call the large system size regime, reaching it for the first time in the laboratory, which we think is important to make progress on this problem. And these user facilities are really providing an essential resource, and without which this type of research would just not be possible. Yeah, so we're interested to study these explosive plasma physics phenomenon which occur out in the cosmos. So many places in the universe, we have plasmas interacting and rapidly converting energy from one form to the other. And eventually this creates bright objects releasing high energy photons, and that's what we see from far away. But some examples of this are the interaction of the solar wind with the Earth's magnetosphere. There's a magnetized solar wind that blows continuously out from the sun. And when it impinges on objects in the solar system, such as the Earth and the Earth's magnetosphere, there's a very strong magnetized interaction between those two things. And it can drive many phenomena, including shocks and magnetic reconnection. Similarly, solar flares occur closer to the surface of the sun. And you can actually see these loops are observed with spacecraft and ground telescopes. It's just showing that the plasma close to the surface of the sun is strongly magnetized. These loops follow the magnetic field poking out of the sun. And these are very highly dynamic, and these loops move around with time. And occasionally, these equilibrium are interrupted very quickly, and this magnetic energy is converted to particle energy, and it rapidly heats up the corona and drives processes such as solar flares, which lead to very extreme brightening of the sun. But it's still a mystery. We don't really deeply understand how fast this energy can be converted to plasma kinetic energy. There's also phenomena like particle acceleration in shocks. Out in space, we observe supernova that explode, and it drives a giant shock into the intervening medium outside the shock that's just sitting there in space. The shocks can be very thin, as you can see from these images that we get in the X-rays. But we also see that there's very significant particle acceleration in these shocks. We believe this is where the highest energy cosmic rays in the universe are accelerated. And we can also see that locally to these shocks, electrons and ions get accelerated to very, very high energy. But there's lots of mysteries about how these shocks behave and how they can accelerate particles to such high energy. And finally, we're getting ever new and more dramatic observations, such as these recent observations of the black hole accretion disk around M87, which has been observed with the Event Horizon Telescope. We can see now that near this black hole, there's a very hot mass of swirling, highly turbulent, hot plasma. And again, we'd like to understand how these fundamental processes can be heating up the plasma to these enormous temperatures. So people always ask, what does it mean to do a plasma experiment in the laboratory that has some relevance to astrophysics? So, I mean, fortunately, though, we know that the laws of fluid dynamics are what are called scale invariant. The same physics that applies to a swirling cup of coffee also applies to the ocean and can also apply to extreme scales. So the main key question when you're trying to do a scaled experiment or a scaled understanding of a phenomenon is to understand what are the dimensionless parameters of the system, and how do you study what's called a scaled or a similar system. And to do this, we have to understand what we think are the basic physics behind it and determine what are the important dimensionless parameters. And this has a long history in fluid dynamics research, but the same ideas apply in plasma physics research. Plasma is more complicated, so we get more dimensionless parameters that we need to understand and match. In these magnetized systems, there are several dimensionless parameters that I'll come back to mentioning today. One is measuring the system size compared to certain parameters which are related to the plasma kinetic, what I call kinetic or micro scales. One of them is the particle gyro radius rho, and this is the radius that a particle, how fast the particle moves away from a magnetic field line. If you have a magnetic field line threading through a plasma, the particles tend to have a helical orbit following the magnetic field. And so they stick very close to that field line, but this gyro radius is how far they actually can, how far their excursion is from that field line. There's also a related parameter, which is the collisionless skin depth. And this is when certain waves in the plasma transition to a kinetic version of the wave. And this is also the scale where energy dissipation happens very efficiently in the plasma. So we want to understand the scaling, and we want to make a plasma a certain system size compared to these dimensionless parameters. There's also dimensionless parameters related to the Mach number of the flow, and the plasma beta, which is the relation of the plasma pressure to the magnetic pressure. If you have freedom to choose your density, temperature, system size, you can match many of these parameters compared to certain astrophysical systems. The caveat, of course, is that some parameters are very hard to match, but we can only match them in regime. Like this is also common in fluid physics, where the Reynolds number may be matched only in regime, like it's 10 to the 8th in this large physical system, but we can match it and get 10 to the 4 in the laboratory. But we think for some physically motivated reason that that's a reasonable match, and we're still going to gain some physics insight from it. So lasers produce really interesting plasmas to do this type of plasma physics research with. Many of these experiments start with just a laser impinging onto a target. At an experiment like Omega and NIF, you can couple 1 kilojoule all the way up to a megajoule of energy into small volumes of order a few cubic or few square millimeters on a target, or a few cubic millimeters in space in a few nanoseconds. So this is sufficient to take that solid material and convert it into a very high temperature plasma within just a few nanoseconds. The laser typically propagates into a region in the plume that's at a density that's called the critical density, which is the maximum depth that the laser can propagate to. And from that point, it drives this what's called ablation wave, where that plasma expands out from there. And the plasma that expands out can be very hot. It can be of order 1 to 10 keV, which is of order 10 to 100 million degrees Kelvin. The plasma flow is of order of 100 kilometers per second, and a large range of densities can be, found depending on where you are in this system, but it's typically fairly large, of order 10 to the 18 or 10 to the 20 particles per cubic centimeter. This is a very high temperature. It's a low collisionality plasma. It has high magnetic Reynolds number, which means that magnetic fields are dissipated very slowly in these systems. So it's very good for astrophysics research. So yeah, these laser facilities produce very interesting plasmas for plasma astrophysics questions. We have many questions that we're interested in answering: magnetic reconnection and collisionless shocks, as I've mentioned. And in general, we have when we design these, we may have a set of desired properties we want to get to. But in general, when we have a large laser energy, we can choose to use this energy to obtain simultaneously large density, temperature, and system size in various combinations at the same time. And then depending how you choose the density, temperature, and size, you can optimize towards one or another of these parameters, including getting to a high magnetic Reynolds number, which is related to low magnetic dissipation in the system. We can also choose parameters to get a large scale separation of the system size versus the ion skin depth, as I mentioned before. This is important for the shock and magnetic reconnection problems that I mentioned. You can also get velocities of order and larger than the sound speed to get supersonic flows and shocks. Just want to show quickly that how these lab experiments can produce some interesting and complementary data to astrophysical observations. We observe solar flares on the sun through telescopes and spacecraft X-ray observations on telescopes, and these produce really exciting observations. You see these large explosions on the sun, and also we can observe the X-ray photons coming out, and we can see that very high energy particle populations must have been accelerated during these solar flares, and this is based on these hard spectra of X-rays that we observe from these regions. So we can see these phenomena are happening, and we can get these beautiful videos at the global scale, but we're really not resolving the kinetic scales in the plasma at all. The scale of the ion gyro radius or electron gyro radius would be way smaller than 1 pixel on these images. So we're not seeing the fundamental processes, we're just seeing the global effects. There's also a set of spacecraft measurements that are being made as well these days. There's very exciting data coming from the Cluster and MMS spacecraft, which are a set of 4 spacecraft that are orbiting in formation around the Earth, traveling through different regions of the magnetosphere. They travel through both what's called the bow shock of the Earth, which is where the solar wind first impinges and interacts with the magnetosphere and sees the magnetic reconnection and shock regions there. And it also traverses in the magnetotail, which is another location where magnetic reconnection can occur. These spacecraft are producing really incredibly detailed observations, but one can argue that these are actually too zoomed in. With just a few point measurements, it can be very difficult to situate how these measurements are being made in the context of these fully evolving 3D turbulent plasmas. There have been another set of laboratory experiments that I've been involved in what I call discharge plasmas. And these are plasmas that are generated by magnetic induction, and they have scales of, the vacuum chamber is about 1 meter big, but it makes a plasma at a much lower density than these laser experiments, and the magnetic fields are much weaker. So even though the physical system size is larger, it's turned out that the normalized system size, once you compare it to these ion skin depth or ion gyro radius, these are actually smaller. We can make very detailed measurements of plasma behavior in these systems based on probes. So we can get high quality 2D and 3D measurements and understand much better about how the reconnection process is happening in these plasmas. However, it's also very zoomed in for some of the for what we want to do as the next step. So this is where we are, and it brings us to these laser plasma experiments. And so I'll come to these in just a minute now that we're getting there. But we can now make reconnection regions and magnetic reconnection current sheets that are getting to a very large system size with system size of order 100 or 200 ion skin depths, which is comparable to the magnetosphere. And we can do this with imaging diagnostics, which are bridging global and local scales. So a little bit just about magnetic reconnection now that I've mentioned it multiple times. The main idea with magnetic reconnection is if you can bring regions of opposite magnetic field very close to each other in a plasma, it forms, first of all, something called a current sheet, which is a very high plasma current flowing that's separating these regions of opposite magnetic field. And through the reconnection process, you can imagine it that these magnetic field lines can be cut here and rejoin with each other and then snap and release their energy into the downstream either way. So this process can release magnetic energy and drive plasma flows and energization. And ultimately, you're converting stored magnetic energy to particle kinetic energy. And this is implicated in many locations that we care about. First of all, we're very interested in the solar wind magnetosphere interaction in space. This process can govern the interaction of the solar wind with the magnetosphere. And we now have increasingly more technology up in space. And all of this technology, it's at risk to adverse space weather, they call it. So this is a reason we need to understand this process and how it fits into space weather around the Earth. Solar flares, as I've mentioned, is also a system or a topic where we think reconnection is rapidly converting energy to plasma energy. The largest solar flares can energize particles on the sun to greater than 1 MeV. And there's a long-standing hypothesis that very small-scale magnetic reconnection in what are called nanoflares heats the solar corona and ultimately is what drives the solar wind. There's also ideas from simulations that even in these shock systems, that there's reconnection happening in the turbulence near the shock, and that's ultimately responsible for all of this particle acceleration we observe in shocks. Finally, connecting to other plasma systems that we do with these laser experiments, we know that magnetic fields can modify how the plasma behaves in Hall realms on other NIF experiments. And so ultimately, we think that some of these ideas from these experiments can provide some insights on other applications of laser plasmas. So really, these frontier questions we're after are how can we get fast magnetic reconnection and fast energy conversion in large systems? And there's two hypotheses that we're after that have been predicted in simulations and given hints at from other experiments over the years. One is there's a phenomenon called momentum transport, which can occur if you can make a very, very thin current sheet such that the electrons meandering motion in this current sheet can take their momentum from the center of the current sheet out to the edge. So this is one proposed mechanism of how you can sustain a very large electric field in these plasmas and allow a rapid energy conversion. Another set of hypotheses is the phenomenon of what are called plasmoid instability or plasmoid turbulence, which is another instability of these long current sheets. And the fact that this current sheet actually doesn't stay as a smooth or laminar structure, but actually gets broken up into many clumps. This is believed and shown in simulations to accelerate the energy conversion process. And so both of these are things we think we can see in the laboratory. They both require going to very large systems and also while maintaining a very high conductivity plasma. So we want to get to both a large system size, which I've called L over DI, where DI is the ion skin depth, and low resistivity, which is parameterized by a number we call the Lundquist number. And this idea is motivating several new experiments in plasma physics these days, including discharge type laboratory experiments and pulse power experiments. And our group has been working on doing this with laser experiments. So I'll talk for a few minutes about our experiments at the NIF. So we've provided a new experimental technique to do reconnection in these very large system size regime. We have data techniques that allow us to get experimental images of reconnection that span from the global to the kinetic scales. And we're observing on NIF fast magnetic reconnection. We can see that the reconnection rate is much larger than just can be accounted for by classical plasma resistivity. So we think that these phenomena such as momentum transport are coming into it. And this is bolstered by the fact that we can observe with these diagnostics that the current sheet is thinning down to a very narrow scale in the plasma. And it's suggesting that in the data we've analyzed that this momentum transport is playing an important role. Dan, can I ask about timing? I just don't want to go too long. So
yes,
can you give me a time check of how fast to get through the rest of the material?
You still have a few minutes. We can go over a few minutes. Well, there's a couple of questions I wanted to ask you as well. And we have Zach ready to come on at 2:15. So actually, if the conversation fills to that time, that's really our hard stop. Or excuse me, I should say, yes, 2:15 Eastern time.
Oh, okay. Okay, great. All right. Thank you. Okay, a little bit more about how these experiments work. So I mentioned before how a laser generates a high temperature plasma. It also generates magnetic field. When the laser impinges on a solid, it's a very energetic and non-equilibrium type of phenomenon. And as a result, you can have things that you don't expect from classical thermodynamics. In particular, you can get temperature gradients and density gradients that are pointed in different directions. In this case, the density gradient tends to point toward this solid target where all this plasma is coming from, but the temperature gradient is pointing towards the laser focus. And so this situation arises because you have just such strong non-equilibrium heating of the system. And this can produce a magnetic field by something called the Biermann battery effect. And it occurs when these two, when the density and temperature are not collinear with one another. And this can produce multiple Tesla of magnetic field. In our experiments, we observe creation of order 10 to 20 Tesla of magnetic field generated in these plasmas. This is a very strong magnetic field. It's stronger or just about as strong as you could ever produce in the laboratory by a static conductors. And this, interestingly enough, this Biermann battery process is also believed to be the phenomenon that produces magnetic field early in the evolution of the universe. And in that case, this non-uniform heating would happen due to shocks in the plasma, but here it's being driven by a laser. And so you can now imagine putting two of these plumes next to each other, and they'll each generate their own magnetic field, and then we can collide them into one another. And that's how we drive a magnetic reconnection. When these two plasmas interact and collide with each other, it will drive together their magnetic fields, which, based on the geometry, are opposite to one another. So it can drive reconnection. And this has been done in many experiments over the past decade or so. Here, this is a proton radiography image, which I'll come back to and explain briefly. But basically, you can see two plasmas here that are expanding, and there's this interaction region between them, which is this magnetic reconnection current sheet. We're now also doing 3D kinetic simulations of this, where the simulation includes both this magnetic field generation phase and the reconnection phase. So here's a simulation where we have two plumes expanding nearby to one another, and they've collided with one another and are interacting. And this green region I highlight here is a region in the simulation which is showing significant J.E, which is current times electric field. So this is a magnetic energy conversion. So this region is where magnetic energy is being converted back to plasma energy. So we're doing these experiments at the NIF to study magnetic reconnection in very highly extended current sheets. As I mentioned, we want to get to this large system size regime. And to do that at NIF, we use the fact that NIF has a lot of laser beams to play with. It has 192 laser beams over all 4 pi of the spherical vacuum chamber. We use a subset of those which can all focus down onto a one-sided target and produce a nice smooth spots. But what we've done in these experiments is tiled 2 sets of beams onto a flat target to produce 2 highly extended plumes. These generate their magnetic field by the Biermann battery effect and then collide in this central region here. If you look at this from the side on, we have two plasma plumes that are expanding. They have opposite fields and they're going to collide in this central region here. We have several diagnostics we use to measure this. We have a gated X-ray detector, which measures the plasma self-emission, and you can see how the plasma evolves in space with that. We also have a diagnostic called Proton Radiography, which uses a beam of high-energy protons, and those protons go through this geometry, and they're bent by whatever electric and magnetic fields are there, and then imaged on a detector. And we have ways to analyze that data to infer what the magnetic fields were in the experiment and how they're evolving. This is just a soft X-ray image of the footprints of those lasers to show that we've made two extended plumes that are next to each other. So I just wanted, since you guys are having a user facility discussion, I just wanted to give a few comments about how it's been to interact with the NIF facility for these experiments. So NIF is really an invaluable resource to run these experiments. As a youngish person, it's really amazing to tap and leverage the resources of such a facility to do these experiments. They would never be possible as a single PI or even in a small project. These experiments literally are requiring the interaction of dozens of people on the facility. And the same goes true with experiments we've done at Omega, which are really a joy to run. The facility provides enormous resources for these. In the case of NIF, there's the facility is providing this enormous laser with up to megajoules of energy, 192 laser beams, a suite of diagnostics that have been developed over the years for many experiments, which are validated and run in their different regimes. NIF and Omega also provide target engineering, and in some cases, the manufacturing of the target. This is important because you may need a very precise target to get the physics you want, and there's engineers and manufacturing that produce the target for you. In turn, I'd like to think that we've provided important things for the facility. We've proposed new diagnostics, we've validated diagnostic measurements and extended diagnostics into new regimes. So I think it's a useful overall collaboration where these external users provide new ideas for the facility. NIF also has a user community. There's a NIF user group with annual meetings. Omega also has a laser user group with multiple annual get-togethers where people share results and talk about the evolution of the facility. And of course, also there's support from the DOE Office of Science and NSA. Okay, so back to the experiments. So we've developed these imaging diagnostics, which can give us pictures of the evolution of these systems, bridging from the global to the local kinetic scales. We have these side-on X-ray imaging diagnostics. So you can see here is the two plumes being driven by the lasers, and this central region here is actually where these two plumes are colliding with one another. So we can see that the plasma there is getting bright. The plasma is actually heating up in this region, and it's actually getting more dense as well. So we can image this current sheet formation from the side on. There's also optical interferometry and refraction diagnostics that show how these plasmas are interacting. We can even see the generation of some turbulence and instabilities where these plasmas are interacting. And this proton radiography, which I'll show you now, are how we measure how these magnetic fields evolve in space and time. So I mentioned this, but this is just showing more of these images of the current sheet formation and the brightening through the X-rays that we observe from the end on. So we can see the sequence where the central structure here is getting brighter and longer as these plumes interact. So there's a conversion of energy to the plasma where they're interacting. This is also useful. We have some techniques to take these images and back out what the plasma temperature must have been. And that's useful for understanding what are the parameters in the plasma near the reconnection regions for comparing to our theoretical expectations. So proton radiography, I've mentioned, is a technique to measure the electric and magnetic fields in the plasma. And these experiments, what we do is we have a separate fusion implosion that's run nearby to our main plasma physics experiment. So NIF is very good at doing fusion. And so one thing you can do is have a small capsule filled with deuterium and helium-3 and compress that with a number of lasers. And when it fully implodes, it creates a burst of fusion protons which go in all directions. Some of them will go through your plasma of interest, and those protons will be, their trajectory will be bent by whatever magnetic fields you've got there. And then, so they pick up a deflection through your plasma, and then they're imaged on a detector. And you can work through the theory of it. And these deflections are proportional to the line integrated Lorentz forces on those protons as they go through your plasma. So there's both a magnetic force and an electric force. You can show that the electric force is very small. So really these deflections are related to the magnetic field. And then you can quantitatively analyze this with one of two ways. One is if you can put some mesh in between here and you break your proton beam up into a large number of beamlets, you can track how far each of these beamlets moved from its default position and determine what the angles were from that and get your magnetic fields. There's a more powerful method now that we've been developing, which is not to do a mesh image, but to just have a simple fluence image. And so these deflections will actually cause focusing and defocusing of protons on the detector. And that gives you intensity variations, and you can do a mathematical inversion of that and get the magnetic fields at high spatial resolution. We've been obtaining some really beautiful proton radiographs from NIF that we've been analyzing, and I'll just show you qualitatively what we're seeing here. So you can see here these two plumes. And remember, we had two nicely long tiled sets of beams. So each of these dark bands is a region of proton focusing around each one of those plumes by this global Biermann battery magnetic field. But we can also see where these plumes interact. There's a region of very low proton fluence, that's this white region, and that is a defocusing of the protons caused by this very strong current sheet that's forming between those. And so in that region, the magnetic field from one plume to the other is reversing over a very narrow region, and that has the effect of defocusing the protons and leads to a low fluence on the detector. So this white region here is direct evidence that there's a current sheet that's been formed. We've developed these analysis techniques.
Excuse me, Will, this is Dan. We got 5 minutes.
Okay, I think I'm just about to wrap it up. So yeah, so we can quantitatively analyze these proton fluence variations that we observe and infer the magnetic field profiles and the plasma current profiles in the reconnection region. We can also produce full magnetic field maps of these interacting plasmas. So you can see we have a region of strong magnetic field pointing one direction on one side and reversing over a very, very narrow region to the other. And we can also see from this analysis that this current sheet is getting to an extremely narrow scale. It's only about 25 microns. So it's this very narrow current sheet in this global system. And so we've produced a current sheet with a really enormous aspect ratio where the length in this direction is about 100 times the width. And this is comparable to what's being produced naturally in space, such as in the Earth's magnetotail. We can process this data also and estimate that reconnection, very fast reconnection can occur due to how narrow the current sheet has thinned to via these momentum transport mechanisms that I mentioned earlier. Okay, and I think this is about where I'll wrap up. So we've generated and produced platforms to do magnetic reconnection experiments for the National Ignition Facility. And at NIF, we can tile these lasers to produce a very highly extended 1D current and developed high quality reconstructions and ways to analyze our magnetic field data, which span from the global to the kinetic scales. We have getting a number of physics results from these experiments. We have much more data as well that we've started to analyze from our sequence of experiments. So we're very excited about this whole sequence of experiments, and we thank the NIF facility, for all of the support for these experiments. So yeah, thank you very much.
All right, awesome. Thank you very much, Will. That is some really fascinating detail, getting down into how the different experiments have worked. And I appreciate you making the reference to both Omega and NIF and the different types of benefits you've seen in working with the two facilities.
Mhm.
You mentioned in more detail some of what you have been able to access in terms of the technology at NIF, like with 192 lasers that they have there, laser beams for you to use. Would there be a particular kind of distinction between Omega and NIF, or perhaps other user facilities, if you've ever used them, that you would speak to? I'm thinking more in a positive way in terms of the network of these different facilities would each offer slightly different types of capacities or capabilities for you.
Yeah, so let's see. So first of all, maybe it's easiest to speak about some of the uniqueness of them. So first of all, overall, Omega and NIF are together, they're unique in being able to produce these very high quality, large system size magnetic reconnection systems. Omega, you can put about 1 kilojoule or so into each of these plasma bubbles, and that allows you to reach certain density and temperature conditions. And NIF, you can put, in our geometry, about 20 beams tiled onto the target. So you can get to a much larger system, and you can also get to higher laser energies and laser intensities for this type of problem. So going between them, there's a scan that you can do that lets you explore how this behaves under different conditions. One other change is that with the NIF, since you can tile them in such a long, into those two long plumes, you get a nice, what I call 1D interaction between those two plumes that I've shown. And that simplifies the analysis a lot. And it also changes the physics as well. So we've been enjoying comparing the results from the two experiments. There are a number of other lasers in the US, but they're primarily at higher intensity, but lower energy in the plasma. There's a network called LaserNet US with many several user facilities that are supported by FES. Most of those lasers are in the 1 to 10 joule range, but they can also go to higher laser intensity. So those could get to magnetic reconnection regimes, and especially start to study things like relativistic plasmas due to their high intensity. But you can't get to the same large system size regime that we've been after in these experiments.
Okay. Well, thank you very much for all that detail. Yeah. We're going to move on to the next session here, but I really appreciate your time and this insight. Your comments about particularly how the different facilities have been a resource for you is really helpful. And give you actually, I should pass on a hello and a thanks from Kevin Fournier. It's put in a note to you. Thanks for making the time during the SSURF Annual Meeting.
Yeah. Thank you for inviting me.
All right, you're welcome.
Take care.
And for other people watching the session, Kevin that I mentioned is with the National Ignition Facility. He's one of our board members, very helpful in helping get this session ready.